Let me show you the top 10 most important things for you to know about trigonometry. Must know number 1, similar triangles. Similar triangles are triangles that have the exact same shape, but might have different sizes. Let me draw 2 triangles so you can see what I mean. Now I've started by drawing these 2 triangles the exact same size and shape, so they're congruent. If I were to take triangle DEF and make it smaller without changing any of its angles, so keep the shape the exact same, it is still similar to triangle ABC. And similar triangles have 2 very important properties. Their pairs of corresponding angles are equal. So in these 2 triangles, you can see that angle A and D are equal to each other, B and E are equal, and C and F are equal. The other important property is that ratios of corresponding sides are also equal. So the ratio of side AB to side DE would be equal to the ratio of side AC to DF, which would be equal to the ratio of side BC to EF. And we can use these properties to solve for missing sides and angles in triangles that are similar to each other. Let me show you an example. In this question, we're asked to solve for the length of x. In order to do that, I'll have to use these 2 similar triangles that I see, the big triangle and the smaller triangle within it. We'll have to start by proving they're similar, which there are 3 ways to prove similarity. You can do angle-angle similarity, just find 2 pairs of equal angles. Side-side-side similarity, where you show that the ratios of all 3 pairs of sides are equal. Or side-angle-side similarity, where you find 2 equal ratios of pairs of sides and 1 matching pair of angles. For this question, we can do angle-angle similarity. If you know your angle theorems, we have 2 parallel lines here, connected by this side. I know that the angles inside of that F pattern, called corresponding angles, are equal to each other. So I could say that angle D is equal to angle B. Same thing on the other side of the triangle. I know that these angles in here are equal to each other, so angle E equals angle C. And then of course the 2 triangles both share angle A. So based on all 3 pairs of angles being equal, I know the triangles are the same shape. So I could say that triangle DEA is similar to triangle BCA. And because I know that they're similar, I know that the ratios of corresponding sides have to be equal to each other. So I know that the length of BC divided by the length of DE is going to be equal to the length of BA divided by the length of DA. And then if I sub into this equation what I know, I can then solve this equation using algebra. I can cross multiply. 10 times 6 is 60, and 4 times x plus 6 is 4x plus 24. Solving this for x, I'd have 36 equals 4x, divide the 4, I have x equals 9. There you go. Now you can see how to use properties of similar triangles to solve for unknowns. Must know number 2, SOHCAHTOA. This is an acronym that helps you remember the 3 primary trig ratios. Let me draw a right triangle. In this right triangle, I've indicated the 90-degree angle. And then I've labeled one of the acute angles, angle theta. We'll call that the reference angle. All other right triangles with this same reference angle theta would be similar to each other, right? No matter how much I change the size of this triangle, as long as I keep that angle theta the same, it has the exact same shape, meaning the triangles are similar. Which means, based on what we know about similar triangles, they would have the same ratios of corresponding sides. In any right triangle, there are 3 sides. Let's name them. The longest side of a right triangle is always called the hypotenuse. I'll label that H. The side across from our reference angle theta, we'll call that the opposite side. I'll call it O. And the side touching our reference angle theta, we'll call that the adjacent side because it's right beside our reference angle. I'll label that A. Because there are 3 sides, there are 3 different pairs we could make of these 3 sides. That's why you see 3 ratios in SOHCAHTOA. If we find the ratio of the side opposite from the reference angle divided by the hypotenuse, we call that the sine ratio. Cosine of the reference angle is the adjacent side divided by the hypotenuse. And tan is a function that means we're looking at the ratio of the opposite side divided by the adjacent side. Now these primary ratios can be used to find a missing side or a missing angle of a right triangle. Let me show you both examples. Let's look at this first example where we're going to solve for a missing side, x. I notice it's a right triangle with a reference angle of 40. All right triangles with a reference angle of 40 are similar to each other. They all have the same ratios of sides. So whatever x divided by 8 is, will be the same ratio of all other right triangles with a reference angle of 40. So let's communicate that. From 40, the side we're looking for is adjacent to it, and 8 is the longest side of the right triangle, so that's the hypotenuse. The function that involves adjacent and hypotenuse is cosine. So I know cosine of 40 degrees equals the adjacent side, x, divided by the hypotenuse, 8. Your calculator has stored within it what the ratio of adjacent over hypotenuse is for all right triangles with a reference angle of 40. If you typed cosine of 40 degrees on your calculator, it'll give you that ratio. And then we can just multiply the 8 to the other side of that ratio to isolate x. SOHCAHTOA can also be used to find a missing angle inside of a right triangle. If we're looking for this angle here, notice that 8 is opposite from it, and 17 is across from the right angle, so that's the hypotenuse. The ratio that involves opposite and hypotenuse is the sine ratio. So I could say sine of the angle equals the opposite side, 8, divided by the hypotenuse, 17. Now, all right triangles that have an opposite over hypotenuse ratio of 8 over 17 are similar to each other, which means they've all got the same angles, so we can solve for angle theta. Your calculator will be able to tell you if you use the inverse sine function, which is sometimes called arcsine, of 8 over 17. By using the inverse sine function, you're telling your calculator that you are inputting the ratio and looking for the angle. And your calculator would tell you that the angle is about 28.07 degrees. So that's how you use SOHCAHTOA to find a missing side or a missing angle. Must know number 3, sine law and cosine law. Now, not all triangles you work with are going to have a 90-degree angle. If they don't, the only way you'll be able to solve for a missing side or angle is by using sine law or cosine law. Cosine law has two versions. One version if we're solving for a missing side, and one version that is just a rearranged version of it where we're solving for a missing angle. And then there's sine law, which just tells you the ratio of any side divided by sine of its opposite angle is equal. Cosine law has two scenarios where it's used, and sine law has two scenarios where it's used. So I'll show you each scenario of both of these. The scenario where we use cosine law to find a side length is when you know two sides and the angle contained by those two sides in a triangle. So notice in this triangle we know two sides and the angle contained by those two sides, so we could solve for the opposite angle using cosine law. If I follow the pattern of cosine law, it tells me that the unknown side squared equals the sum of the squares of the other two sides minus 2 times the product of the known sides times cosine of the angle contained by the two sides. That will tell you what x squared equals. To get x, make sure you square root whatever this value is. And in this question, it's about 19.96. Let me shrink this and let's do another question. This rearranged version of cosine law is used to solve for an angle if you know all three sides of an oblique triangle. If I'm looking for this angle theta, when I use this cosine law, the important thing to notice is that the side that starts in the numerator is the one opposite from the angle you're looking for. So if I'm finding cosine of theta, the side opposite from theta is 13. So I must start with 13 squared, and then subtract the squares of the other two sides, and then divide by -2 times the second two sides, 14 and 16. This will give us what cosine theta is equal to, and when we know the ratio and want the angle, we would do inverse cosine of that ratio, and it'll give us the angle. And we would get an angle of about 50.82 degrees. Sine law can be used when you know two sides and an angle opposite from one of the two sides. Based on sine law, I know that the ratio of 64 divided by sine of its opposite angle would be equal to the ratio of 42 divided by sine of its opposite angle. And then algebraically, we could rearrange this to isolate sine theta, and then do inverse sine of that ratio, and you would get the angle, which is about 60.93 degrees. The other scenario where you would use sine law is if you know two of the angles and one of the sides. In this triangle, I know that x divided by sine of its opposite angle, 47, would be equal to 5 divided by sine of its opposite angle, 51. If you rearrange to isolate x, you would find out that the value of x is about 4.71 units. And there you go. Now you know how to use sine law and cosine law to solve for missing sides and angles of oblique triangles. Must know number 4, the special triangles. There are two special triangles that are going to allow you to find exact values of sine, cos, and tan for a few special angles. Let me construct those triangles for you. The first one is an isosceles right triangle. If this triangle is isosceles, I know that the two legs of the right triangle are equal in length. I could assign them both a length of 1. And I know these two angles would have to be equal to each other, and since they both add to 90, I know they're both 45 degrees. If I use Pythagorean theorem to solve for the length of the hypotenuse, I would get the square root of 2. And then I could use these dimensions to figure out the sine, cos, and tan ratios for 45. Now, not all right triangles with a reference angle of 45 are going to have lengths of 1, 1, and root 2, but their ratios of lengths would all be the same because all the triangles, no matter how big or small, would have the same shape, meaning the same ratios. Let's assume that this 45 is our reference angle. That would make this opposite, this adjacent, this hypotenuse. Let me write the three primary ratios for 45 degrees. Sine of 45 degrees is opposite over hypotenuse, so 1 over root 2. Cosine of 45 is adjacent over hypotenuse, which is also 1 over root 2. And tan of 45 is opposite over adjacent, which is 1 over 1, which is just 1. Now, the sine and cosine ratios have a square root in their denominators. You should rationalize those denominators, and you can do that by multiplying top and bottom of both of those fractions by root 2. So those are the exact values for sine, cos, and tan of 45 degrees. The other special triangle is a half equilateral triangle. If this equilateral triangle started off with all side lengths being 2, and of course all the angles being equal, so they would all be 60. If I cut this equilateral triangle in half, that 60-degree angle that was at the top of this triangle gets bisected into two 30-degree angles, and the side at the bottom also gets bisected, so this length is 1. Now, I don't actually need the left half of this triangle, so I'm going to erase it, and then I could use Pythagorean theorem to solve for that side, and I would find out its length is equal to the square root of 3. And now I notice there are two angles in here that I could find the exact values of their sine, cos, and tan ratios. If I start by finding the ratios for the 30-degree reference angle, so sine of 30 is opposite over hypotenuse, which is a half. Cos of 30 is adjacent over hypotenuse, which is root 3 over 2. And tan of 30 is opposite over adjacent, which is 1 over root 3. But if we rationalize that by multiplying top and bottom by root 3, you get root 3 over 3. Now, if we make 60 the reference angle, sine of 60 would be opposite over hypotenuse, so root 3 over 2. Cos of 60 is adjacent over hypotenuse, so 1 over 2. And tan of 60 is opposite over adjacent, which is root 3 over 1, which is just root 3. So there you go. If you ever want a primary ratio for either 30, 45, or 60, you can use your special triangles to find the exact values of those ratios. Must know number 5, cast rule and the unit circle. These tools are going to broaden your understanding of trigonometry and allow you to start using it for angles bigger than angles you would find inside of a triangle. Let's start with the unit circle. I've started by drawing a Cartesian grid, and on this Cartesian grid, I'm going to label the positive x-axis 0 degrees, and then moving in a counterclockwise direction, I'm going to label 90, 180, 270, and then coterminal with 0 degrees would be 360 degrees. The reason why I label them like that is because when we think of angles now, we're not going to think of them as angles in a triangle, but we're going to think of an initial arm, which starts on the positive x-axis, and then rotates some angle counterclockwise in a circle away from that positive x-axis. So if you rotated 90 degrees, you would be up here, 180 here, 270 here, 360 back to where we started, which is why we say it's coterminal with 0 degrees. Now, wherever that initial arm finishes, we call that its terminal arm. And if we know where that terminal arm intersects a circle that has a radius of 1, that actually tells us a lot about its sine, cos, and tan ratios. Let me show you by drawing a circle that has a radius of 1. And I should also mention that this unit circle, whose radius is 1, it's centered at the origin. Now, this yellow terminal arm has rotated some angle theta. So I'm going to label that angle theta, and then I'm going to construct a right angle triangle inside of this circle. This point that it intersects the unit circle at is some xy point. If this is point xy, then I know to get to that point, I would go x units that way, and then y units that way. So I could label this triangle side lengths of x and y. And because this is a unit circle, I know the radius of that circle is 1. Now, if you remember SOHCAHTOA, you would be able to write the sine, cosine, and tan ratios for angle theta based on the side lengths of this triangle that we see inside of the unit circle. Sine of theta equals the opposite side, y, divided by the hypotenuse, 1. And y divided by 1 is just y. Cosine of theta equals the adjacent side divided by the hypotenuse. So x divided by 1, which is just x. And tan of theta is opposite over adjacent, so y divided by x. So the important thing you need to notice is the sine ratio of angle theta is equal to the y-coordinate of where you intersect the unit circle. And cosine of theta is equal to the x-coordinate of where the terminal arm intersects the unit circle. So if we know the point where the terminal arm intersects the unit circle, then we in fact know the cosine and sine ratios for angle theta. So I could say that point xy is equal to cos theta, comma, sine theta. And what points on this unit circle will we know the coordinates of? Well, because the radius is 1, I know moving 1 unit in all of those 4 directions, I could label 4 points on this unit circle. This point would be the point 1, 0. Up here is the point 0, 1. Here's negative 1, 0. And here's 0, negative 1. So if I asked you to find sine of 90 degrees, you wouldn't have to ask a calculator. If you rotated 90 degrees, your terminal arm would intersect the unit circle at that point right there. And the sine ratio is equal to the y-coordinate of where you intersect the unit circle. So sine of 90 is equal to 1. Let me test you with one more. What if I asked you to find cosine of 270 degrees? If you rotated 270 degrees, your terminal arm would intersect the unit circle at this point right here. And the cosine ratio is equal to the x-coordinate. So cosine of 270 is equal to 0. Let's look at another tool which is very directly related to this unit circle. This tool is called the CAST rule, and it's just an acronym that helps you remember what ratios are positive in each quadrant. And for the CAST rule, you write C, A, S, T in each of those quadrants. I've also heard people say all students take calculus to help you remember that acronym. But what these letters tell you is in each of these quadrants, which ratios are positive. A stands for all. And then, of course, S is for sine, T is for tan, and C is for cosine. And then why does this make sense? Well, if we think back to the unit circle, I know that the y-coordinate of where you intersect the unit circle is the sine ratio. Where are y-coordinates positive? Above the x-axis in quadrant 1 and 2. That's why the CAST rule tells us in quadrant 1, sine is positive, and in quadrant 2, sine is also positive. And where are y-coordinates negative? That's below the x-axis in quadrant 3 and 4. That's why in those quadrants, sine would be negative. Only tan is positive in quadrant 3, and only cosine is positive in quadrant 4. And cosine is equal to the x-coordinate of where you intersect the unit circle, and where are x-coordinates positive in quadrant 1 and 4. And CAST rule tells us in quadrant 1, cos is positive, in quadrant 4, cos is positive. But in quadrant 2 and 3, only sine and tan are positive, meaning cosine would be negative in both those quadrants. Hopefully you understand how the unit circle and CAST rule can be useful, and in the next couple sections, I'll show you how we can actually use them. Must know number 6. You need to be able to find the exact value of ratios for angles that are bigger than 90 degrees. To do that, you're going to need to remember your special triangles and the unit circle. Let me draw those quickly as a reminder. Let's say you are asked to find the exact value of the sine ratio of 150 degrees. The first thing you want to do is figure out where that principal angle of 150 degrees falls on a Cartesian grid. A principal angle of 150 degrees means from the positive x-axis, rotate counterclockwise 150 degrees. And that would land you about right here. The angle from positive x counterclockwise to that terminal arm is 150. Now each principal angle has a reference angle. The reference angle is the angle between the terminal arm and the closest x-axis. The reference angle is the angle between the terminal arm and the closest x-axis. The angle between 150 and 180 would be 30 degrees. So I could say that the reference angle is 30 degrees. This reference angle and the cast rule is going to help me find